we're going to talk about internal energy. All right, internal energy, it's symbolized by the symbol U, and it kind of just refers to that kinetic energy and that potential energy at like a really, really microscopic scale. So let's say I have a system. All right, the system is just whatever you want to observe in the universe. Well, the surroundings is it's everything else that's not the system, right? Now, the system can have molecules, right? And these molecules, they're going to have potential energy stored in the bonds. These molecules are going to be moving, so they're going to have kinetic energy. And basically, the sum of the kinetic energies and those potential energies are going to define the internal energy of the system. Now, specifically, in chemistry, we're more interested in the change in internal energy. And the change in internal energy is going to be given by this formula. Internal energy is going to be equal to heat plus the work. All right, so Q stands for heat, W stands for work, and I'll show you how they relate to internal energy. Let's start off with a simple example that we all know. Let's say that if the system is 100 degrees Celsius, and let's say that the surroundings is 25 degrees Celsius, heat is going to flow from the system to the surroundings. So as a result, the molecules inside the system are going to start moving slower. Because think about it. At a really high temperature, right, molecules are going to be moving fast. But at a lower temperature, when the system kind of expends some of its heat to the surroundings, right, because remember, heat flows from hot to cold. So when the system loses heat, well, you're essentially losing kinetic energy, right, the energy of motion among these particles. These particles are going to move slower. They're not going to move as fast. So we can see that when our heat is getting transferred from our system to the surroundings, so our system is losing heat, you can see that our internal energy is going to decrease. And the same is true. If our surroundings is hotter than the system, the surroundings will transfer energy to the system. And in that case, the system, the particles are getting faster, right, and all that. So as the heat increases, our internal energy is going to increase. Now, let's take a look at another example. And this is going to have to do with work. You might be saying, how is work related to chemistry? I mean, I heard of work in physics. How is work related in chemistry? Say we have a system and we have a couple of particles in here, gas particles. Gas particles are going to push up on the system or on this piston. So let's say that we have these gas particles, they push up on the piston and then the piston moves up. Well, we can see that the system is doing work. So work is done. So right now the work is done by the system. Now what's happening when the work is done by the system? The system is using some of its energy in order to move this piston up. So as a result, the internal energy will decrease. Meanwhile, if work is done on a system, right? So let's say instead of the gas particles pushing down on the piston, let's say if it was the piston pushing down on the gas particles. So work is done on the system by the surroundings. Well, what's going to happen is these gas particles are essentially going to slam into the piston with essentially increased energy, right? Because think about it. It's kind of like you're slamming into a wall that's kind of like pushing you forward, right? You're going to be like bouncing back with higher energy. I know that's kind of like a weird analogy, but I can't really think of any analogies right now. So think about it, right? You're bumping into the wall, but then the wall is moving super duper fast at you. So you're going to be bumping backwards at a faster speed. And therefore, that's actually going to increase the internal energy of the system. So when work is done by the system, your internal energy is going to decrease because you're expending energy to do work. While when work is done on a system, the internal energy will increase because, well, I kind of just showed it with that example. And so if you're using this formula to calculate the change in internal energy, you just have to be mindful that if the system is gaining, if heat is being transferred from the surroundings to the system, this is going to be positive because it's gaining internal energy. And if work is done, let's say, on the system, this is also going to be positive. So you kind of just have to add these two values up and then you get your answer. So that's kind of how it goes. But the most important idea to get here is the sign convention. So when heat is flowing out of the system, Q is going to be negative. when heat is flowing into the system, Q is going to be positive, and then you have these two scenarios for work. So that is the main takeaway from this lesson.